So it really is a pleasure to be here at this marvelous conference. It's been an incredibly stimulating week, and I've learned a lot. You know, in recent years, I've been going to a lot of fancy occasions where I'm usually among the youngest. And at those occasions, I look around at my distinguished colleagues, and I see my future. And it's depressing. So one of the nice things about this conference is that I'm among the oldest, and I look around at my colleagues, and I see the future of string theory. And it's exciting. So I'm delighted to be here. And this has been a wonderful conference, and I've learned a lot. And I'm not going to thank the organizers for inviting me to give this summary talk, because it's not a pleasant task. And I can't do justice in half an hour to the marvelous results we've heard. And I can't even begin to compete with Dycraft's marvelous summary last year, but he had a whole hour. So, and I have to save time for the joke, so it's going to be a bit of a hurry, but luckily I'm last and I can deal with John. So let me just start with the jokes, because otherwise I might get cut off. You know, I like to collect cartoons about string theory, and in my public lectures I used to show this cartoon, which appeared in the New Yorker years ago, which I always thought was really nice, that the public regarded string theory on the same level as Greek. It's all string theory to me, she says. But recently there have been a spate of cartoons, as well as other things, but you know, let's focus on the cartoons, that are a little disturbing. For example, there's this one that somebody gave me. It says, there's this character here you might recognize, who says, "Carl, I got a big funding request for string theory. Is string theory consistent with intelligent design?" And Carl says, "Yes, string theory is consistent with anything. It all depends on what kind of universe we are. If you fund it, it just confirms that it's consistent with intelligent design." I like it. This is really easy to fund. And then there was this other cartoon recently in the New Yorker. I wonder what led to this one. This guy walking by Harvey's place. "Tonight, 5 to 8 is string theory bullshit." Well, I was pretty depressed by this sequence, this evolution in the stringy cartoons, until somebody sent me an advertisement that appeared in the New York Times Magazine. "String theory, when physics gets physical." So I was pleased to see that string theory was resuming its rightful place in popular culture. Well, this has been, in fact, a wonderful conference that anyone who doubts that string theory remains vital even when it's not in the midst of another revolution, and that there are many areas in which great progress is being made, can be reassured, as I was. And I'm going to briefly run through the contributions and maybe say a word or two about a few of them, what struck me, but I have very little time, of course, to do justice to any of them. And there were quite a few topics. I mean, it really is amazing the number of different approaches to and applications now of string theory. This conference was a little less mathematical than the last one, I noticed, but maybe that's because Yao wasn't involved in organizing it. And one of the main still, after 10 years, one of the main driving forces in the field as a whole, and where some of the most exciting results have occurred, is good old ADS-CFT and its application to conformal field theory, and in particular to super-Yang-Mills theory. And if I had to choose anything that I thought was sort of the most impressive calculation and achievement over the last year, it was the almost solution of large N super-Yang-Mills theory. I mean, it's still a lot to be done, but I don't think anyone doubts that eventually, and probably pretty soon, sooner than we had reason to hope for, N equals 4 super-Yang-Mills theory will be solved. And in fact, in the sense of large strings or sort of large operators, not worried about the boundary effects, it has been due to the work of Weishart and many others, and I'm only referring here to the authors of the papers that were presented here, otherwise it would get out of hand. And that, I think, is a remarkable development, very beautiful, and we've already seen that it has applications all over the place and will continue to do so. So the integrability of both sides and the properties of the gauge theory and the string theory have been used in a very interdependent way to construct this analytic, this major step towards an analytic solution of the large N gauge theory. That's a marvelous achievement. And we heard not just only of that, but of other contributions to this subject, which are proceeding at rapid pace. The talk of Zarembo, many tests and developments and calculations of using the string, world sheet scattering. And then we heard a totally new idea, which again struck me enormously, that of Juan Maldacena, on an extension of the repertoire of tricks of ADS-CFT to include open string scattering amplitudes, which correspond to on-shell gluon scattering amplitudes in the dual Yang-Mills theory, which, even though they are colored objects, but still physical because they're on shell, and even though they suffer from horrible infrared divergences, can be meaningfully discussed, regularized, and calculated, and compared with these beautiful conjectures that were derived by Byrne and his friends using inspired guesses, and can be alternatively calculated using the integrability of Yang-Mills theory. So I particularly find it amazingly beautiful that the Yang-Mills scattering amplitudes can be calculated by for strong coupling by a classical trajectory of strings in the bulk, a saddle point in the world sheet calculation. And I am sure that this beautiful development that Juan reported on will lead to a whole host of new applications in ADS-CFT. We also heard just today a rather cute ADS-CFT derivation of a version of the Skerm model for describing baryons in the dual string theory as instantons. And I must say that once again, this makes me feel optimistic that maybe in my lifetime we will finally see the QCD string in some better version than this lattice gauge theory simulation. But already the ADS-CFT and the duality between open and closed strings, conformal field theories, and string theory is beginning to be applied to real systems, to real QCD, although only approximately with little control. And as we heard during the conference, and some very interesting contributions, perhaps to other real systems in nature that our condensed matter friends construct or imagine. These applications are absolutely wonderful and, of course, very important since they do illustrate the vitality of string theory, not just as a field of mathematics all off to itself, but part of the rest of science and able to contribute to other fields in science. So, of course, there are the wonderful applications of these ideas to quantum chromodynamics, where some surprising results have been derived for transport coefficients that might have something to do with Rick physics. And we heard about that in two lovely talks. And Kovtun gave a whole very general pitch for the applicability of conformal field theory to a whole host of problems, including Rick physics, but also including quantum phase transitions in perhaps realizable condensed matter systems. And we heard a very imaginative talk by Sun-Young Ray on quantum phase transitions that might be modeled using CFT, ADS-CFT, and probed in graphene. So this is absolutely lovely development, and who knows, as Joe Polchinski remarked to me yesterday, maybe ADS-CFT will solve high TC superconductivity. That would be great, but seems unlikely to me. This correspondence between gauge theory and string theory is just an incredible source of two-way information. We learn a lot about string theory from gauge theory and vice versa. However, to a large extent, it's gone this way. We use string theory or more usually supergravity. But in the case of some of the recent developments I described, string theory itself has been used quite heavily to learn about gauge theory, whereas the implications of what we know about gauge theory for string theory have been less developed, partly because we just don't know how to formulate good questions in string theory or quantum gravity. So there are lots of areas of gauge theories which we understand extremely well, like low energy, weak coupling, Yang-Mills theory. And that should tell us something about string theory on highly curved manifolds, but we don't know what the right questions. So how can you exploit that incredible amount of information you have for weak coupling, Yang-Mills theory? And so somehow we have to learn how to ask the right questions. Once you can ask the right questions, like black hole physics, we know how to ask the right questions, and there are lots you can learn, then you have the answers right there. But so the problem here is not in strengthening this connection, is in knowing how to ask questions wisely about quantum gravity. We heard about experiment. In fact, the first talk of the conference was on the upcoming LHC and its prospects and why it was delayed and so on. And then there were a whole bunch of talks which directly confronted experiment, either more traditional particle physics phenomenology, such as Naudi Seiberg's talk, which I really found amusing because faced with the little mass hierarchy of problem, noted down-to-earth phenomenologists like Nima Arkani Hamed have invented dramatic scenarios which led to astounding conclusions like the anthropic principle, whereas highfalutin, top-down theorists like Nati Seiberg added a dimension 5 operator and cured the problem. I found the contrast quite amusing and was highly relieved. Joe Polchinski gave a beautiful summary of his and others' work on cosmic strings, which is one of the great hopes of actually seeing fundamental strings in the sky. It turns out to be an extremely hard and complex problem, and we just have to hope that they're there and can be observed. It's one of the great hopes of direct evidence for string theory. We heard a wonderful talk just now by Provetto on semi-realistic models, which are now being compared in detail with LHC scenarios. And from Lisa, we heard that black holes are probably not going to be seen, even if the gravity and string scale is low, which is very unlikely anyway, but if it's not too high, there could be stringy and gravitational effects that could be detected with more care. A lot of work has been gone into exploring the landscape, the multiplicity of string solutions or metastable vacua, and I'm just going to flash these. Charlikins and Becker and Shami and Michael Douglas. Beautiful work in exploring the multitude of approximate solutions of string theory and more. I think about a quarter of the talks were exploring various aspects of the landscape or a phenomena, different kinds of ways of breaking supersymmetry or adding corrections to the simplest descriptions of those solutions. Stimulated by work on metastable vacua in quantum field theory that break supersymmetry or not just lift non-perturbative effects in supersymmetric vacua, people have looked for those in the landscape and found them and studied them. Both Hiroshi and Kumran gave very interesting talks on realizing or trying to discuss the metastable vacua of the type that Seiberg and collaborators have discussed in the string landscape. And of course, there's lots of work on black holes. There's always lots of work on black holes, but it's really quite beautiful. We heard about new solutions and new kinds of black holes. Incredible zoo of black holes in higher dimensions. Roberto Emperan. We saw a beautiful discussion of emergent geometry by De Boer, who constructed BPS geometries and showed that the most likely ones are black hole-like and could analyze them. It's a lovely example of emergent geometry, in this case the geometry of black holes. And a wonderful calculations by Ashok Sen, who was able to really count and explore the black holes with all sorts of charges. more black holes, and more black holes, some problems, enigmas, more black holes. Black holes in the landscape seem to be very little, but some really a review of some very beautiful stuff, again, which has progressed rapidly in the last year, but really the breakthrough happened last year, a year before, which Martin Zweibach reported on in following Schnabel's work, actually being able to control the solutions in many interesting cases to open string field theory and to begin to develop the techniques to probe off-shell amplitudes and closed string amplitudes soon. And a set of interesting ideas and potential applications of the pure spinor formalism were reviewed by Nathan Berkovich. And then under the category of miscellaneous, because they had no common theme, but therefore they tend to be very innovative, new ideas. Of course, we had Ed's revisiting of 2 + 1 dimensional gravity, where he proposed a particular conformal field theory, which might give a complete dual description of the system. And Andy's search for the holographic dual of a heterotic stack of strings, which looks like a very complicated conformal field theory with W algebras, but might lead to a whole new kind of duality. And Eva's discussion of the emergence of extra dimensions in time-dependent solutions from wrapped winding strings on around cycles of negatively curved compactified spaces, which has all sorts of directions to evolve. So these are all rather new miscellaneous ideas. And finally, we heard discussion of the ultraviolet behavior just today of supergravity and string theory. And Zvi's claim that n = 8 supergravity is finite. We actually at lunch discussed a bet. Well, I tried to challenge him to a bet, but we couldn't decide on the terms of the bet. But he seems convinced, and he has very interesting ideas as to why, and evidence that this might be true. And I was I was trying to finish my talk during Rousseau's talks. I wasn't sure whether he agreed with that, but it sounded like that for other stringy reasons, Rousseau and collaborators are also arguing that the pure supergravity theory, for some mysterious stringy reason, is also finite. And then finally, we heard about string theory and cosmology and its application to inflationary theories. We had a beautiful talk about the state of observational cosmology, and then an explanation by Andre Lindy. And we heard a interesting discussion of attempt to make anthropic arguments precise, if not respectable, by Raphael. And similarly, Renata discussed how to various models of supergravity and string compactifications that could be tested by measurements of cosmological measurements. Which finishes my rapid review, and now I have to go even more rapidly through my comments on string theory and where we stand. So, the poster for this conference, I think, does summarize a bit the situation in string theory, which is probably why it was chosen, because it's clear if you look at this poster and the blindfolded man who is trying to find the truth with a stick has no idea what he's doing. And to some extent, neither do we. We still don't really know what string theory is. So when I give a public lectures nowadays, as I will tomorrow, I boast about how string theory does all these wonderful things, but I have to say, I have to be honest, because, it's been 40 years and still can't tell experimenters how to falsify it, so I do talk about the failures of string theory, and I say that we don't really understand what it is. We have these ways of doing calculations, but we don't know what the principles are. And I think that's why the poster was chosen to be what it is, and we're not sure what is missing. Why can't we define what string theory is? Well, string theory now seems to be not different than almost any four-dimensional gauge theory, at least any four-dimensional conformally invariant gauge theory. Probably any four-dimensional theory that's consistent. So, that general framework of quantum field theory isn't really a theory either. It's a framework. Is string theory a theory or a framework? If it's a framework, what are we missing to make it into a predictive theory? Maybe if we're missing something, and no matter how much you believe in the landscape, if you don't know what the theory is, you can't believe that it is final. So we're missing something, and that might lead to a unique solution. The unique solution is not a vacuum, a metastable state, it's a cosmology, and one perhaps which can't be formulated in terms of ordinary space-time, most of us tend to believe. And so, to quote an astute political commentator in the United States, Bill Maher, what are the new rules? Most of you didn't get that joke. Well, I don't know what the new rules are, but it's not just that we might suspect that we have to formulate string theory in some formulation that doesn't involve space-time from the beginning, but also that we're faced with describing the whole universe. And, the universe is not a metastable static state that happens to be here for a few billion years. It's the whole space-time history. And I don't think we have any idea what the rules are, when we have to deal with the beginning, which is a real problem, but also the boundary conditions, and also the end, as Ed has stressed strongly, It's not just the problem of the beginning, it's a problem of the end. If the end doesn't make sense, we don't really know how to formulate observables. So for most of the things we talk about, we don't know what we're talking about. We don't know what the framework is or the theory is, and we don't know what the rules of the game are. That's why I'm not too upset by these pictures, because they're all based on assuming that, well, we might not know what the rules of the game are, but we can assume they're just like the old rules and just go ahead. And that used to be the opinion of my colleagues as well. And the real reason I think that some people take these anthropic arguments seriously, of course, is this cosmological constant. How do we explain that? There's no question in my mind that if we could explain this, 90% of the anthropists would disavow the A principle. And this is a small number, right? Because usually it's stated to be 10 to the minus 64. How do you, well, of course we all believe in supersymmetry. But it's not really 10 to the minus 64, remember. That's an energy density. In normal units, it's 10 to the minus 16 as an energy, a mass, a length. Now, 10 to the minus 16 is not such a small number. We've explained small numbers or large numbers of this size or even bigger before. Remember, Dirac had another large number that he was very worried about. That number is related not to lambda, one of the terms in Einstein's action, but to G Newton. He was worried about why is the Planck mass so much bigger than the proton mass. And that's a smaller number by a factor of 1,000. And Dirac was really concerned about this. No possibility of explaining it, so it had to be related to other arguments, to other features of the universe. He did not invoke anthropic arguments, although it would have been easy to do so. Believe me, if this number wasn't 10, it was of order 1, we wouldn't be here. But he didn't invoke anthropic arguments. He found another big number. It had to do with the size of the universe, and that varied with time, so he made a prediction. A real prediction. You could falsify his anthropic, his large number hypothesis. And indeed, it was falsified. Because G dot doesn't vary. It's non-zero, and alpha dot's non-zero. But anyway, we solved this number in particle physics 30 years ago. It's called QCD. The proton mass, compared to the unification, the basic scale of physics, is just that mass that's produced when the coupling runs, and it runs logarithmically. So it's really the log of this number that we have to explain, runs to be big enough to confine the quarks and produce the scale and produce the mass. So we essentially understand this number within a order of magnitude or so. And it's not the only large, small number we've actually understood. We understand the hierarchy, which is similar to the cosmological constant, we think. Supersymmetry, again, logarithms make this explainable with a symmetry principle now, not a dynamical principle. And we also even understand other small numbers like the neutrino masses via another mechanism, the seesaw mechanism. And all these numbers are of order the cosmological constant number. And they're no big deals once we understand them. They were for Dirac, but now we understand them. So the problem is not that this number is so small. It's that we don't have an explanation. And we haven't thought of any mechanism. But remember one thing, those of you who are still tempted by anthropic arguments, just because you don't know the explanation doesn't mean it doesn't exist. And I have to share with you a poem, another popular culture manifestation of the debates in string theory that I discovered in The Nation last Christmas, called The Anthropic Principle. It's a lovely poem, and let me just read you part of it. So she in her poem, she says, after a while, so 3 drinks later, back in the office, I blast facts out my manifesto, which is simple. We should all relax. Apparently, no matter what we do, we already do our part. We balance the cosmological constant just by getting up in the morning and smacking around our wives. Isn't that amazing? And here's how it works according to the anthropic principle. There could be an infinity of universes, starry bubbles, burning balls, solid boxes of hard time. You name it, and they made it. Some are gelatinous, some are inside out, but there's only one commonality. None are peopled. None have us. Only the composition of our universe allows for our existence. In fact, our presence is required, or the whole thing falls apart. So here is what I think. What if we all held our breath and stood sidewise in a corner so we couldn't be found? our universe would go wailing through the empty corridors of physics, knocking over furnitures and pictures, searching for its vanished friends. And afterwards, when we said, "Gotcha," and the universe wept with relief, we could all sit down for a nice cup of something comfy and have a heart-to-heart, and someone somewhere might wise up. So, just beautiful comment on what poets think of the entropic principle. So my suggestion, I don't know, it could be right, and we will never understand the cosmological constant or the precise parameters of the solution of string theory. But the only thing to do, of course, is what we always do. Even if you believe in the entropic principle, and observe. And luckily, as everyone has remarked, we're close to being able to observe. This is coming, and right on its heels is Strings 08 at CERN. And a year later, there might even be real data in Strings 09 in Rome, which raises the question, where is Strings 10? Now this conference must go on, because it's sort of like the canary in the mine. If this conference, which no one is organizing except volunteers like our present organizers who were kind enough and brave enough to organize this, that would be a bad sign for string theory. So I have a few suggestions. There's, of course, Korea, which has already talked about it and would be a lovely site for a strings conference in 2010. And then there's a very strong string community in Israel, which would be a lovely place for a strings conference. Just throwing out some ideas. And finally, there's the good old USA, which hasn't had one for a while. And if I look around the good old USA, there are two places that I think morally deserve to run the conference. So just a few ideas. And let me end with just muchas gracias to the organizers of this conference for all the hard work they did in making this such a wonderful week, and of course to the staff.